we should start now. Yes.
Vou começar, então, falar para eles desligarem. Alguém que eu vou começar aqui, rapidinho, vai filmar? Alô, alô? Pronto, tá funcionando. Boa tarde a todos. A gente teve a honra de receber essa semana o professor Hussein, da Universidade de Lille, né? Ele está como professor de visitante no nosso programa de geotecnia. E é um programa de uma cátedra francesa, do consulado francês com a USP, né, com o estado de São Paulo. E o professor veio de Lille para ajudar nossos colegas aqui na pós-graduação e também para dar cursos, palestras, etc., né, durante 2 semanas. E essa é a segunda palestra, ele deu uma semana passada na Poli, em São Paulo, né? E o professor Hussein, ele tem mais que 30 anos de professor, desde 99, na área numérica, né? Geotecnia, com túneis, com várias coisas, já, com tudo que é geotecnia, e faz já uns 15 anos que ele trabalha com essa parte de energia geotérmica, tá? Mas ele tem uma larga experiência, né? E o professor Hussein já teve mais que 30 orientados de doutorado, etc. Tem uma lista, o currículo dele é muito grande. Já vou direto para a apresentação, né? E, professor Hussein, thank you very much for coming.
I understood everything.
You understand? Oh. Good.
Thank you. Oh, wait, yes. It's a little bit sound, you know? Yeah. Thank you very much. Thank you, Professor Cristina, for this invitation. Thank you. I'm looking for Fernando for giving me this opportunity. Thank you to all of you for being there. Hello, everyone. Yes, so I will introduce today a topic we are sharing together with Professor Cristina about energy geostructures. Maybe you have ever heard about it, most of you, but I will give also an overview of this new technology and also how it works and what are the remaining challenges that we need to overcome in order to improve our knowledge about this technology and also in order to help fostering this technology, to promote it at a larger scale for builders, for the end users, for the persons in the community who have to decide how to deal with this energy transition. So this is one of the technology I would like to present to you today. The overview of my presentation today will follow this, the following topics. I will start by introducing myself a little bit about me, my university, and my city in France. And then we will talk more about science and technology. And for those who have already attended the presentation I gave last week, don't worry, it is a different one. So there will be some overlapping, but you will see some new topics. Yes, maybe you already presented this, Cristina, no? More or less, yes. I'm full professor at the University of Lille since 2011 like the Politecnico in Sao Paulo, School of Engineers. We have the same within our university. Doing my research in the laboratory which is called LGCGE, Civil Engineering and Geo-Environment. I hold a PhD about tunnels in urban areas, mainly numerical modeling, and also what we call here accreditation of doctoral supervision, also about numerical modeling of soil structure interaction problems. This is my research area. You already gave this, so maybe I can pass. So yes, let me start by presenting University of Lille first, and then we will talk about science. This is some key elements about University of Lille. University of Lille, it is now the 3rd biggest city in France, but we have some scale effect between France and Brazil. So you will see that what I call 3rd city, it is for you here a very small village. But nevertheless, saying that, at the University of Lille, we have something like 80,000 students, which is quite a very big university, about all the topics from law, medicine, technology, everything. I will present it. And we are around 7,200 staff members, including researchers, professors, and also academic and also administrative position here in this number. Among these 80,000 students, we have mainly 10,000 international students, which is also quite a very good rate. And we receive for about 151 different nationality for our students. So you see that the University of Lille is a very international university. Blah, blah, blah. We have, what is important, we have 24 different locations. Like your university, you have one here, one other location in Sao Paulo maybe, and some. We have 24 different locations for the University of Lille, mainly around the city. Not really outside the city, but mainly around the city, and 15 faculties, or what we call schools and institutes. This is how it is organized at the University of Lille. We have what we call faculties. It is written in French, but it's Latin language, so it's easy to understand. Faculties, law, psychology, health, language, culture, society, humanities, science and technology, economics. And we have what we call in France some institutes and schools, and I belong to this one, Polytechnique, which is a kind of faculty of engineering. But in France, since we practice engineering, we don't talk about faculty, we talk about school, escuela, école, escuela. It's right, no? Yeah. A little bit about our history. Lille, it's a very old city, and University of Lille has a very ancient knowledge. The first steps of the University of Lille started, you see, in the 16th century. So this is the first topic, the first University of Lille. It was built in 1559, mainly starting from law and then developing medicines and so on and blah, blah, blah. So this is quite important to know. It's that the University of Lille is a very old university. Some other evolution, but maybe it's not important to talk about them. Just to explain, just to see how the university have grown up over years and over the necessity of the society. Talking about industrial and textile worker, because in north of France, we had this very well knowledge about textile workers. This was in north of France the main center in France working about textile. That's why they opened some schools, and then we merged some faculties of art, science, and so on. And this is for our history. Let's talk about our public figures. Very famous one. Maybe you know this guy, no? Pasteur. You know who is Pasteur? Pasteur was the first dean of the University of Science and Technology in Lille. That was beginning in 1854. So we have some famous persons coming from the University of Lille. Pasteur. But not only Pasteur. Who has a geotechnical background? Yes, you are PhD students. The master students. You ever heard about Boussinesq, no? You know who is Boussinesq. Boussinesq was also a professor at University of Lille. So you see, we had Boussinesq, and now they have me. But please, no comparison, okay? Boussinesq was professor at the University of Lille, and also maybe you don't know who is Albert Calmette and Camille Guérin, but they have invented something that all of you have in your body, the vaccine, BCG. You know what? You know this vaccine has been invented and developed at the University of Lille. So we are quite proud to talk about this when we present our university. You see, this is the past. Our present figures. I'm not going to talk about. Because we are not going to talk about us, but we can talk about our students. Who are our famous students? We have some sports at the University of Lille has a very strong importance. So we have some very famous students. This student, Anna Gomis, was Olympic bronze medalist in the Olympic game in Athens in 2004. And Iris was also one of our students at the University of Lille, not so far, 10 years ago. She was elected Miss France and also Miss Universe. So we are also quite proud to have some beautiful women. It's not only in Brazil that we found beautiful women, but also in France and at the University of Lille. Okay, it was a joke, but let's talk about now, let's talk about Lille. Lille, as I told you, my city, it's about the third biggest city in France, 1.2 million. So for you, it's very small, I know. But 1.2 million for Lille, 80,000 students. So you imagine Lille it's like maybe São Carlos. It's a very student city. We have many, many students in Lille. Not only our 80,000, because in Lille you have also some other universities, some private universities, quite famous. And at total, we have like more than, more than 115,000 students in the University of Lille. And this is the third most attractive city in terms of job and housing. Why I'm saying that? It's because many of the students that have studied in Lille stay in Lille to work, because Lille is a very pleasant city. And those who find some job outside Lille, mainly in Paris, they also stay living in Lille, and they take every day, daily, a train to go from Lille to Paris, because Lille is also a very convenient place. We are far from Paris by about 1 hour per train, and we have like 10 to 15 trains per day, direct connection between Lille and Paris, 1 hour by train. In 1 hour, you reach the city center of Paris from the city center of Lille. So it's very convenient, 1 hour. So people prefer stay in Lille because, you know, also housing is much more, it's less expensive. It's cheaper. So they prefer living in Lille and working in Paris. But Lille, it's also very convenient because we have some very good connection with European cities. We have a good connection with London by direct train under the Channel, you know, 1 hour and 20 minutes. We are close to Brussels, half an hour by train. So it's very easy. And we have also direct connection from Lille to all main cities in France by direct connection train without any changing. So it's a very convenient place. And the last but not the least, also Lille is also a city of art and history. This is a very famous place that reflecting the Spanish occupation, because you have to know that Lille was occupied by Spain for years, for centuries. And at that moment, there was a war between Spain and the Flemish, you know, for this zone. And this place has been constructed. It's a fortress, yeah, fortress that has been built. By Vauban, who was a colonel in France. He received the order from the King Louis XIV. Maybe you heard about Louis XIV. Louis XIV asked Vauban to build this fortress to protect the city. So this is inside Lille. And in order to achieve the construction in a very quick way, they decided to collect the material for the buildings from the city, not outside, not waiting for materials coming from a place to another place, because at that moment it was quite a long, complicated travel to move the materials. So Vauban asked someone that all of you know, Coulon. You know who is Coulon? And Coulon designed this fortress. This was the first work at that moment, the premises of the design of retaining walls. You know what is retaining walls. You all maybe have learned how to design retaining walls and diaphragm walls. The first construction was this one. So the first work of Coulon, and then all the others that came after, started from this place. And those who will have chance to come to visit France, you definitely will go there and you will see how it was built. And the materials that have been used for constructing, because I was talking about materials, they picked the chalk. You know what is chalk? La craie. That we used to. Yes. Because the underground of the city is mainly composed of chalk, so they decided to use this chalk to build this fortress. So this is a little history. Okay, now we change. We are going to start talking about geothermal energy. We all know what is geothermal energy. Before talking about geothermal energy, let's have just an overview of energy usage. Why it is important today for you, young, for the future, for us also, to talk about energy usage and why it is important to look for some solution. You have to know that nowadays in Europe, but maybe it's maybe not the same use here, but in Europe, you have to know that if we add this need for heating and cooling and for hot water, 73% of the energy is being used for heating and cooling and hot water. So it's quite important. And up to now, the main technology that has been used, it's the energy coming from the fossil, fuels, gas, and so on. So the idea is to reduce the carbon footprint and also to prevent, due also to the fact that every house in Europe, it's an average, okay? But every house is responsible for about 20 tons of greenhouse gas emission, which is very important. And because it's a very big challenge for our society today and tomorrow, people, scientists, engineers have had to look for a new, affordable, renewable solution to reduce this carbon footprint and also to change our use. Okay, and we see how it grows also for over years. And if we see that mainly about this 73%, mainly it's coming from services here. So all the buildings, like our buildings here at the university, are some very consuming building. Yesterday night, I was walking here at the university, coming back from the place. And I was surprised to see that there was a building, all the lights were open, and there were no one inside. So when I talk that we need to change some use, it's part of what we need to do. And then we have to look for some solution. Among the solution we are trying to promote, we talk about this geothermal sources. Geothermal, I will just present. It's not something new. Geothermal energy has been used for decades and maybe also for centuries. We did not invent nothing. Okay, we see here from the 20 years ago up to today and the projection for tomorrow, we see that heat pump and geothermal energy has a real increase and a real potentiality in terms of preventing this energy demand. What is geothermal? Geothermal energy, it's because it's something that is free. It's just behind our feet. We know that if we look on our planet, Earth, we know that 99% of this planet is at a very high temperature, more than 1,000 degrees. So it's something free that is, and it can cover the estimation about more than 1 million years of the needs in terms of energy demand. And it's free. So people decided to use this, but we did not invent nothing. In fact, when you think, what we are doing now, even for 20 years ago, we are just trying to improve what our ancient people have already developed. We know that our ancient civilization were also very intelligent. They have discovered. We have discovered nothing. We are just re-implementing, reusing what they have done in another way. Okay, but we have to think that we are just working on how to re-implement, reintegrate this technology that is very ancient. We have some, let's say, 4,000 before Christ. They were already using the geothermal energy. So it is not something new. How we could use it? We have several ways. When we talk about geothermal energy, we have several ways. We can use the deep. It is written in French, but we have what we call this deep geothermal energy. Deep geothermal energy, it means that you go very deep on the ground, when I'm talking about a very, very deep, oh, sorry, let me go back there. It's about more than here, 2,000 meters. When we go there, we can catch a very high temperature, and with the pressure, we can produce electricity. Okay, electricity. This is deep geothermal energy. When we talk about shallow geothermal energy, what is our concern, together with Professor Christina, when we talk about shallow geothermal energy, we are talking about low enthalpy. You know what is enthalpy in thermodynamics. We are talking about low enthalpy or low energy. This low energy is to use the fact that, if I go back there, the fact that in a very shallow depth, we have quite a constant temperature. And using this, we can, by exchanging the temperature between the ground, the soil, and some technology, we can produce some heat. And apart from the heat, we can also produce, thank you, because it's hot, no? Today is very hot. So we are not talking about deep geothermal, we are talking about shallow. Shallow, it's only to produce heating and cooling. I will show you how, okay? And among this known technology, conventional, we will then work on, as you see here, the integration of ground source heat pump with some geotechnical materials, geotechnical construction to provide some energy. And what is the next step? It's to integrate this shallow geothermal energy within what we call a district heating and cooling network. District, no, maybe not today, but I talk about it. District is to put all this technology together that we could use, all the renewable technologies, inside one unique network, and to provide all the buildings with this technology. No more using this, no more using, you don't use here for heating, but in Europe we use. So what is shallow geothermal energy? Shallow geothermal energy, it's something that is more or less conventional. Conventional technology, it's this one or this one. What we call boreholes. Maybe you know what are the boreholes, or aquifer geothermal energy. This technology is quite well known and well used, but it has some issues. Let's talk about, for instance, borehole. What is borehole? Borehole, you need to have space, you see. So you need to have a available space where you will not be able to build something else. So it's something that you will lose this space for future development. So if you have space, if you are, for instance, someone is building his home now, I'm not looking for someone in special, but it's for someone is building his home and he has a garden, he could put this, but you have some issues because how it works. You have to drill, to do some drilling about 30 centimeters or less, 20 centimeters. And inside, you put some tubes to extract the heat from the ground and to inject it using a ground source heat pump and to transform the heating that you extracted from the soil for heating. Okay? Why it is an issue? Because first, you need some space, as I told you. And secondly, when you drill, you need also to fill. You will use some grout, so it has a carbon impact, a carbon footprint that is not negligible. So this technology, even if it is a quite good technology, has some, let's say, bad issues about this carbon footprint and also about the necessity to have some available space. The same for the aquifer. The aquifer is the same. If you have an aquifer below, a deep aquifer, not so deep, 50 meters, something like this, you can inject some water in one way, some meters far from it, 100 to 200 meters, you extract the water you have injected, and the aquifer will change the temperature of this water, and using the heat pump, you will produce heating, and this is how it works. It has also an issue. It's obvious, no? because you are injecting some temperature in the aquifer, and you may unbalance at the end this temperature, and you may have some environmental issues. So these are the main technologies that are developed right now, that work, but that have some issues to control. And from this, what geotechnical engineers, we, in maybe from the 1980s, so it's now like more than 20 years ago, have this idea to say, okay, instead of implementing these tubes to exchange the heat from the ground, why do not integrate them in the piles that geotechnical engineers are designing? Because in all cases, we are implementing some structural elements, which are piles, diaphragm walls, base slab, tunnels. Every geotechnical structure that is embedded in the ground could become a source of heating. This is how this technology has been implemented 40 years ago, and this is what we are trying to address. So let's talk about this technology. As I told you, what this technology is really interesting for us, because it has, as I told you, as you may understand, it has a dual role. Dual role, that means it has initially a structural role. These structures you see here or here are designed for a structural purpose. Then what you do, you integrate some tubes. Inside these tubes, you will circulate a fluid at a certain temperature. The fluid will interact with the structure, which is mainly composed by concrete. This is the steel cage of a pile. This is a steel cage of lining of a tunnel. This is a steel cage of a diaphragm wall. And in all these structures, you have these tubes where fluid is circulating and interacting with the ground. And why now it becomes very interesting? Because it has a very cost-effective energy, shallow geothermal energy solution. Why it is cost-effective? Because the extra cost of this technology is only composed by what? The cost of the tubes. Because in all cases, you need to have this structural function. In all cases, you will need to pay for the concrete and for the cage. So the extra cost is only coming from this and also the heat pump. But it represents how much for a real case? Like 1 to 5% of the global cost, even less than 5%. So it has a real cost-effective possibility. And also the fact that you are producing geothermal energy, you automatically reduce the carbon footprint. The carbon footprint is coming from what? It's coming from the concrete you use, okay? In all cases, you will put this concrete. And here, by adding a new role for this structure, you reduce the CO2 emission and you save the CO2 emission. And you see here in this graph how the CO2 saving increase with the increase of the technology. So it has a very interesting carbon footprint impact. So this is the technology. And what is now interesting with this technology is that, you remember I told you, maybe I will talk about it later. So this is let's just have a quick overview of, because you are aware of what is done in some experimental sites. You have some here, we have some. But you have to know also that this technology is quite mature. This is what I told you. This is a quite mature technology, and it has been implemented in some real cases, not only buildings, but some very big projects. You have this Zurich airport terminal, which is composed of energy piles. The same for the Google campus in United States. They use this technology. The Crystal Siemens, you have several cases existing. Also in Brazil, I know, but we'll need to update it. let's just quickly, just to give you some inputs about this technology. You see, when I talk about Zurich Airport, the Zurich Airport, okay, it's French, but it will be easy. 306 piles are energy piles among the 441 piles that has been used. And with these piles, the airport was able, this technology was able to provide over 70% of the heat demand, which is not negligible. And the other 30% is coming from, let's say, maybe aerothermal heat pump, so with electricity, but at least they save 70%. What does it represent? It represents that in terms of mazout, it's the fuel they use for heating, it represents like 150,000 liters of mazout saved per year. You see the impact. It represents 400 tons of CO2 saved per year. So it's not negligible, you see? And because of this first success story for at the Zurich airport, they decided they are building now extension of this airport. They have decided to integrate 1,000 new energy piles among this 1,000, and you see almost all the piles will be energy piles because you can combine depending on the energy demand and how you want to design it in the energy point of view. You can decide if you have a project where you have 1,000 piles, you can decide that 70% of them could be energy or not, and so on. Here, they decided that almost 80% of the piles are energy piles in order to cover between 75 to 100% of the energy demand of this extension of the airport. So you see that you have some real cases that demonstrate the feasibility, but not only the feasibility, but also the potentiality of this technology. So this is something quite interesting. I was talking about piles. Here, some real cases. We have also some other real cases about energy walls. You know, these diaphragm walls in Romania. They have some real cases. In the Politecnico di Torino in Italy, they also have this case. These are some real cases, not a small case. Okay, not experimental. You have in France also, this is for a metro station, which is under construction, that will be delivered next year. They also use energy walls for the wall, but also for the basement, you see here, equipped. You have also tunnels application, some new one that has been inaugurated, yes, 3 years ago. Another one here in Germany. So they are existing, but there are still, let's say, some very particular technology because it's not really every day that you build a tunnel and so on, but mainly every day you could find one builder building some piles. This is why we mainly concentrate our knowledge on piles, but also on looking for some other technologies. There are also some other innovative applications. We have this, what we call key walls. I don't know if you know what is this key walls or not. Key walls, you know when you have a river, you want to protect the wall. Usually you use maybe wood panels, no? It's among the rivers. You have, in every place, sometimes they put concrete panels, sometimes they put wall, but in Europe, mainly in Netherlands, but also in north of France, they use metallic structures, which are called key walls. And integrating some energy wall, it is a real positive and innovative technology because this geothermal energy is not only capturing the thermal energy of the ground, but also of the water. So you exchange between the water and the ground. So it's really interesting. We have these tunnels, as I already talked, and we have micropiles. I don't know if you know what is micropile. Okay, micropile, it's a small pile. We know. But among this, when do we use micropile? We use micropile in some specific application, but also in one particular case when you have to retrofit a building. And especially, for instance, when you have a building that may experience some differential settlement. Sometimes you have some buildings that you find some very important cracking. And then you say, oh, what I have to do? I have to reinforce the existing foundation. You are not going to destroy the building. No, you are just going to re-implement on the existing foundation some micropiles. It's a small machine that can enter here and put some micropiles integrated to the existing foundation. So in a retrofitting solution, it is quite interesting to say, okay, what we can do when we have retrofitting application, because this technology has to be implemented, this micropile, we call, we say, okay, because we need to put some micropiles, we could integrate inside some tubes and also use this micropiles as energy. And this technology becomes very close to what you have presented to me in São Paulo. Your metallic one, it's exactly the same. It's exactly the same. It's a small pile like this. You just put one single U inside. That's it. You know the one that you were. It's exactly this. And this is under development in Italy, but also in France. And next year I will start a PhD position working on this topic on a specific, we call challenging material, the chalk. As I told you, you have this chalk. Chalk is a porous media, and we have some challenge to work on the chalk behavior using this technology. So this is something that we will start working on next year. And just to finish with this part and then to go on the physics, because I'm not going to show you all the real cases. We have collected among a project that I am coordinating in Europe. We have a European project which is called foliage. You can look for it, okay? If you put foliage, you will find it. We have collected like 800 real cases over the world. Mainly you see in Europe, in North America. We need to update, but because now we know that there are some cases here in Brazil, and if we make a zoom, we can see the importance of this technology in these countries. We have it here. We have this evolution. You see, as I told you, the piles, it's the major part of the real cases installation in Europe. This is the piles. This represents the piles, and this is a zoom. This is this one. This represents the tunnels, walls, barrette, and sheet pile walls, where energy is also used for, where these systems are used for extracting the heat. And you have the evolution over the years, as you can see. So we have collected this information, and we have more or less this representation, and then we will go on the next step. You see that mainly this technology has been implemented in UK, in Austria, Italy. Where is France? France here. We are not so bad, but we still need to improve. What is the objective? The objective is that all the countries in Europe and even over the world start to use this technology, because we have proved, we know now that this technology works and it is mature. And our work is to promote this technology. So this is what we are looking for, increasing this. That's enough for introducing EGS, what we call energy geostructures. Let's talk about the physics behind this. The physics is so this is now new. For those who have, what is the physics? This figure is really interesting if you take a time to look on it. This figure explains you all the physics behind the technology we are working on. And it explains why we need to continue developing some research. Because, as you understood, energy geostructures, it's a multi-physical problem. You agree? We have thermal exchange. This thermal exchange has a logical interaction with the hydrogeological condition with the ground and the hydraulic potential of the ground. If you have some water, if the soil is saturated, unsaturated, if you have a groundwater flow and so on, we know that heat can be transported by a hydraulic. So you have a strong interaction between thermal and heating. And also, we are all physicians. Mechanics, it's a part of physics. We know that when something is heated or cool, what it happens, it will react. It will expand or contract. So we know that we have also a mechanical interaction. So we have this thermo-hydromechanical interaction that give this problem quite complicated. And this is why, in fact, from the beginning, maybe till 10 years ago, it is still, there are still some issues for the large implementation of the technology, because people are quite afraid of how it would disturb the geological condition, the environmental condition, how it could disturb the behavior of the building, and so on. So we needed, this is what we have done by the 10 last years. We needed to produce some research to look after all these problems. And it's really complicated to proceed, because you have a multi-physical problems. You have the thermal variation that induce thermal stresses. The mechanical also have an influence on the coefficient of thermal expansion, and so on. You see, so if we want, we can discuss about this figure for hours, because this is all the physics we are dealing on, okay? And mainly what we need to do, it's two things. To study this thermo-hydro-mechanical design, okay, to understand. And so we have this mechanical part. We need to understand how it behaves, mechanically speaking. And what we need also, we need to estimate, to calculate the energy performance of the system. If we implement all a system just to say, okay, it costs, I don't know, millions of reals, and then you say, okay, we can just develop, I don't know, 10% of energy demand, it's not good. So we need also to work on this energy design. So this is mainly the two topics we are working on. We are all doing the same. We calculate the amount of energy extracted from the soil or injected, and also how it behaves. This is what we are doing. So we have two main systems. Let's take a look on this first, the thermo-hydraulic principles, this one. If we take a look on it, I took the example of a pile, but whatever we use, it's always the same. What is happening? You remember this is the geothermal flux. You know what is this geothermal flux? It's the heat coming from the center of the earth. So we have this natural heating that help the soil to keep at a constant temperature around. These are some values from France, but here in Brazil it's different. But in France we know that the temperature of the soils varies between 0. This is why I needed a pen. But I'm not going to write here, no. But you know how the temperature evolves. Depending on the outside temperature, you will have a decrease or increase of temperature, and then it will start to become constant, depending on the region in France, in Europe, sorry, from 10 to 15 degrees, it depends. Here in Brazil, it's maybe 20, no? 23 here in Brazil. Yes. In Lille, it's 14. In the south of France, it's 15, 16. In Netherlands, it's 10. You see, it depends, but it's constant. What is important that the temperature, it becomes constant. And then you inject a fluid at a certain temperature. If you inject the fluid, let's say, at a temperature less than the temperature of the soil, what would happen? When the fluid will go out, the temperature of the fluid will increase. Okay? So this delta T, this variation, this positive variation of temperature will create a heating. Injected in the heat pump will enhance, because you know that heat pump have what we call coefficient of performance, COP. So the coefficient of performance of the heat pump will increase this delta T to provide heating demand. So this is what we call, in our case in Europe, winter use. But what is winter for us is not winter for you. It's not the same, I know. But for us, this is what we call winter. And the opposite, on summer, what we do, we inject the temperature at a higher temperature in comparison with the soil. And then if the temperature of the fluid, let's say 30 degrees or 35 degrees, the soil is always at 15, 10 to 15. So the fluid will go out at a lower temperature. You will have a negative delta T that will provide not what we call cooling. Cooling, it's not this. Cooling, it's just refreshment. But it's quite sufficient in our region. So it's really important. And when you do this, what happens? You have some thermal exchanges. You have several thermal exchanges to work on. You have to know that you have a convection of a fluid inside the tubes. Inside these tubes, you have a convection phenomenon. Transport, convection, you know what is convection. It's a transport of heat, of particles of heat between the fluids and the structure. Then you have, between the tubes within the concrete, you have conduction. Conduction, it's transport of heating on a solid material. So you have this conduction. Then what happens when you take into account the soil and the ground and, let's say, the water flow? You have also conduction within the soil mass, in the surrounding soil. We know that the soil will also react. This is exactly what you measure here, and you have some very good results showing that here. And also because of the presence of the water, you have what we call advection. Advection, it's like convection, it's the same, but it's convection with a transport, because it's also moving with the water. What we call it advection. So it's quite complicated to address this issue. It's not so evident when you want, and if you want to then to calculate, as I told you, the energy design, you need to estimate all this phenomenon, which is not so obvious. What we know, because we can discuss about this for hours, but at the end, what you need to know, what we know, it's that the main factors that influence the thermal performance of these energy structures are, first, for sure, the ground, the structure itself, pile, energy wall, tunnels, whatever you want, the internal environment, so the air, or if it's a diaphragmal, the interaction with the inner temperature, if it's a tunnel and so on, and the absorber pipes themselves. When you look on the ground, we know that the factors that are influencing is the ground temperature, as we were saying, okay? The thermal conductivity, we have to calculate it, to measure it. You know how we do or not? Have you ever heard about TRT? They know what is a thermal response test? Some no. So we have some tests, we have some possibilities to estimate it. But you will see that it is not really evident, obvious, because the soil is not it's not so homogeneous as it. The constitution of the soil is quite complicated, and if you have several different layers, I will present it later, you will see that this parameter, which has a very high importance, is not so obvious to determine. You have also the ground saturation. In the simplest way, when we do the calculation, we try to work considering that the soil is fully saturated. But this is not also reality. In reality, the ground saturation has a very big influence. Either you consider non-saturated condition, unsaturated, partially saturated, and so on. The ground uniformity, as I told you, we assume that the ground is a constant, uniform, which is not the case. It is not possible. The ground has a history for centuries. The ground sometimes has been excavated, rebuilt, and so on. So it has a very complicated condition. And you have also, as I told you, the groundwater flow, which has a very big importance. The groundwater flow, the velocity, its direction, and its elevation, the level where it is, all these impact the performance of the energy geostructures. Okay? About the EGS, its shape, if it's a pile, if it's a pile, steel pile, concrete pile, driven pile. All this technology have its importance. The roughness of the structure, if it is a board pile or a driven pile, it's not the same roughness. And the interaction, the connection between the pile and the soil will not be the same. It has an impact on the performance. As I told you, the environmental environment, the airflow regime inside some diaphragm wall, tunnels, the air temperature, the ambient temperature also has an impact. Bruna has shown me some very interesting results showing the importance of the air temperature on the performance. We were discussing on it last week. So we know that all these parameters have an importance. And also, for sure, the absorber pipes, this is what we were talking. The pipes configuration, where we put them, how many we put, how we put them. Spiral, I didn't show some figure, I don't remember. Single U, double U, you have different technology. It has an influence. But you will find some very interesting results in some paper of Professor Christina. So this is something that is already addressed. The pipe diameter also, 20 millimeters, 30, we don't know. The pile embedment and the fluid flow rate. This is also something we discussed. At which speed we need to circulate the fluid. Because if the fluid circulates very quickly, what would happen? We will not have enough time to exchange. And if it is too slow, the performance maybe could also be reduced from the heat pump. So we have to find a real speed. But this is also something you have done, changing and see how it influences. So you see, it's when we need to work, we need to have all this in our mind and to understand how it does. I'm talking too much.
Do you want to take some water?
No, it's okay, I'm fine, don't worry. I will make a little break just after. Some main findings about what I'm saying. You can see it, I'm not going to read it. You can read it yourself. How the ground temperature could influence. These are some results coming from the literature. This is the literature review. About the thermal conductivity, as I was saying. You see, in general, the exchange heat increases with increasing the thermal conductivity. But in some cases, when you have an increase of heat with the thermal, that means that it is maybe more significant in summer, what we call summer, remember, when we inject heating in the soil, this is what we call summer. Maybe if we want to use an international language, we should say extraction or injection. Maybe it's better. Because it's what we call winter, it's not the same for you. And what we call summer, it's not the same, I know. Okay, about the ground saturation also. You can read, you can see that the stored or extracted and the loss of energy, of thermal energy for an energy geostructure in dry soil is lower than in saturated soil. You see? So we know that there are some influences. This is and about the groundwater flow also. The exchange heat increase in a nonlinear way. That means that we need to have some tools that are able to take into account this non-linearity. It's not really obvious. When you do experiments, it's automatically included because it's reality. You are not creating something, you are working with real cases. So all this, it's done. But when we do calculation, when we have to do calculation, we have to take all these into account, which is really a big issue. As a, let's say, conclusion of this, between the two cases, groundwater absence or groundwater presence with or without water, we see that when there is no groundwater, the conduction is the main heat transfer phenomenon. The major effect of the ground, thermal conductivity and limited disturbed region, And in presence of groundwater, you have, as I told you, the combination of conduction and convection or advection with the transport. Major effect of the groundwater velocity. Major effect of the groundwater velocity rather than the effect of the ground thermal conductivity. And we have some regions that are really affected by this thermal exchange, which is called, you know, this panache, the transportation of the heat with the velocity. So the heating is not evolving in a symmetrical way around the geostructure, but you have a dissymmetry of the results. And this has been observed by Marco Barla in 2016, and this is what we also observe when we work on our tunnel results. And this is why when you have a significant values of groundwater flow, then you need to assess correctly the risk of thermal pollution. So these are the main findings about the thermohydraulic principles. Now we have the second way, the thermomechanical one, okay? When we talk about thermomechanical here, you have to keep in mind that we also have the hydraulic condition. So in reality, it's thermohydromechanical principles. What are the factors that influence the thermomechanical principles? You have the thermal operation. This is something we always talk about it. Depending on if you extract or you inject heating, the behavior will not be the same. And also the results depend, we know that the results, the behavior of the energy geostructure depend on the thermal activation time. That means when do you start and how do you start? If you start by extracting or if you start by injecting, it will not behave the same. There is no symmetry. So this is really important when you want to design to see how it happens. And also the ground, the soil permeability. I told you, thermohydro. The soil permeability has an influence. Also, always the thermal conductivity, because the thermal conductivity, this is the parameter that controls the diffusion of the temperature and then the mechanical response. The thermal expansion coefficient now, why we need it? Because this is the parameter that controls how the structure behaves, mechanically speaking. Does it expand, how much it expands, or contract? And also the groundwater flow. As I told you, the velocity and its direction. When we want to design the energy geostructures now, we have something very important to take into account. It's in which initial stress condition the geostructure is when it starts to work. When you do some numerical modeling, maybe some of you have already designed or make some numerical modeling using finite elements. You have to know that when you implement a geostructure, pile, wall, whatever you want, you are disturbing the initial condition because you are extracting some soil to build. Therefore, the initial stress condition is modified by the pile or by the geostructures installation. If you do not take it into account, then you are also hiding an effect. What is the effect of the implementation? Sometimes the effect of the implementation could be not negligible regarding the global behavior. Because the problem is not linear. If the problem is linear, it's not a problem. Linearity means that you have this principle, this superposition principles. If the problem is linear, it's not a problem. The delta T will always be the same, whatever from where you start the initial stress, if it is linear. But if it is not linear, it is really important to know when you exchange heat and when you have some induced thermal stress, you need to know the initial stress condition. If you don't have the initial stress condition, the problem will not work correctly. The same, you have to know that this is the discussion we had with Bruna. The soil structure stiffness ratio, the relative stiffness of the structure regarding the soil has also a very big influence on how the structure is behaving. Because if the structure is quite rigid, it will not work as it is a flexible one. Flexible, imagine you have a very long pile. What you have in São Paulo. The pile will behave like a flexible element. And the interaction with the soil will not be the same. So it's really important to be able to reproduce it. And also the airflow, as we discussed previously. Let's have a quick, are you okay or you want a break? Okay, we continue. Let's talk about this empirical behavior. I choose pile because it's quite easy to reproduce and to catch the physics. What happened? This is the pile that you initially designed for only mechanical purpose. The initial pile. This is how, when you design a pile under axial loading, you have this. You have the settlement of the pile, which is quite constant. You have the induced axial force, and you have the shaft friction, more or less. This is something conventional. What happened when you inject? Sorry, when you inject, that means in the winter mode. In the winter mode, you remember I told you delta T will be negative. So the pile, if the pile is free to behave, it will contract. It will induce some difference of settlement between the upper part and the below part. And this is how the axial force will react. And this is how the shaft friction also will behave. So we see that we need to also really understand and really study what happens here at the interface between the soil and the geostructure, here the pile. And the opposite. In summer mode, when you inject heating and the pile will expand, delta T will be positive, and you will have this variation, the opposite variation. So this is the empirical behavior. If the pile was free to behave, but we know that piles are not free to behave. Why? Because they are connected to the basement, they are connected to the building, so they are not free to behave. The problem is much more complicated. On the basic approach, just to have some idea about the amount of deformation we are talking about of strain. You all know this value of thermal expansion of concrete. It's a well-known value. It's the same for the steel, you know. Otherwise, we cannot put steel into concrete. You know. So if the pile is really free to expand or to contract, what would happen? You will have, for a delta T of 15 degrees, I don't remember this, the length of the pile, but maybe it was 12 meters length of piles. You will have some 1.3 millimeter of free displacement. It's a very small displacement. So you see that mechanically speaking, it's not really a big issue. This is if the pile is free to behave. But in reality, the problem is much more complicated. Why? Because as I told you, here you have a superstructure that is blocking the pile. So the pile will induce some additional effort on the building that we need to estimate. And because of the restraining head condition of the pile, you will have more concentration on the interface between the pile and the soil. And if you have a concentration of stress here, that means that over cycles, over the years, heating, cooling, what you will have? Some sliding effect. Okay? And what could happen, and this is why we have to look after, what could happen, it's these cycles, are they going to introduce a degradation of the condition? And if we have degradation, that means that maybe the pile at the end, after 50 years maybe, the pile will not be able to continue supporting the structure. Imagine. It could be a very big issue. It never happens because we know that this is why we need to work on it. We know that this will not happen, but we need to deal with this problem. We need to, especially when you have some challenging soil condition, as I told you, chalk, or maybe some quick lace, some specific clay where you can have a very big degradation of the condition. And when you do numerical modeling, if you do not take it into account, you will never reproduce it. And it will never happen in your numerical modeling, and you will never see it. You have to pay attention. We have also, when we need to calculate, here we assume that the difference of temperature is constant all over the pile, which is not the case. You did several measures. You know that the delta T is not constant over the length of the pile. And also, the delta T depends on the heat pump, how the heat pump control the need, and also on the environmental condition. All these, you have all these elements you have measured. So you could easily find all this information. We know that the delta T is quite cyclic behavior, but with a very strong nonlinear behavior, because it depends on heating, rest period where the heat pump is not extracting or injecting, then reheating, and after 3 months in Europe, we change heating, cooling, and even you have these daily cycles. It depends on the scale of what you want to study. The cycles are not only per season, heating, cooling, but because even on a day, between the night and the day, you have some cycles. The behavior, it's not the same. So depending on the scale, it becomes very complicated. This is what we call thermal loadings, how to model this. And also the boundaries condition. The boundaries condition is what I was saying. What is the head fixity of the pipe. So how to address this problem? We have mainly 2 ways. The first, experimental approach. Field case, labs, sometimes in real dimensions, sometimes in reduced scale. This is what is done here. Here in Brazil, now I can testify. You have incredible works. It's very good. You have this very good approach. I know. I see it. So I can testify. So this is what you have done. All of what I was talking is addressing here. And then you have numerical approach. I have a numerical background, so I will talk about it. I will not be good to talk about it. Professor Christina will come in France, and she will talk about it at a reverse approach. To address this problem, we have what we call global approaches. Global approaches, you know what it means when you do numerical modeling. Global approach, it's when you integrate the ground and the geostructures in the same model. So it could be axisymmetrical model, it could be 3D, it could be like here in 2D condition or 3D condition. This is more or less complex. It depends on what you want to do. This problem is highly nonlinear, as I told you. This problem is highly nonlinear. And we need to take into account the thermo-hydromechanical condition in the finite element calculation. Let's take a look. What do we need? What do we need to do this model? Who is doing numerical calculation here? Mohammed. Pankish. Who is doing numerical modeling? Okay. You need master students. For the master students that will have to do, you need to represent your ground, to model its behavior. This is what we call constitutive law. You need to have a mechanical or mathematical, it's mainly mathematical, representation on how the soil behaves. If you assume that the soil is behaving linearly, so it's easy. Everything is easy, but this is absolutely not the reality. This is absolutely not the reality. So you need to use a non-linear representation of the soil. You need to model the energy geostructure itself. This one, you need to model it, okay? And in here, you need to know when you model it, if you want to include the pipes or not, because the pipes will control the thermal variation inside. Or maybe on the easiest way, you assume that it's a uniform thermal expansion, which is not, or uniform delta T, which is not reality. You need to also estimate the initial condition, the thermal, because the soil is not at a constant temperature, we know. From the first 6 meters it evolves, then it becomes constant. The environment, so that means for instance, here we assume that the temperature inside here it's constant or not. Maybe it's 20 degrees here and here it's 0 degree because this is the surface if you are on winter. So you need to have this. You need to define the boundaries condition, what we call Dirichlet and Newman. Dirichlet condition, it's how the thermal and the mechanical boundaries are fixed. The lateral is fixed, it doesn't move. The substratum is rigid, it doesn't move. This is what you call Dirichlet boundary condition. Newman is the flux or the loads. So you need to define this correctly. And among the load, these are the mechanical loads, you also have to design correctly, to represent correctly the thermal loading. So you see that it is really not easy. And on the first attempt, you can assume that everything is easy, but it is not the case. I forgot something when I talk about initial condition. Do not forget the initial stress condition. Do you take into account the fact that when you have installed the pile, this is what Pankishu are trying to reproduce. The helical pile, if you want to implement it, we know that it will disturb. Yes, and imagine that after that, you use your helical pile as energy pile. If you do not take into account the modification of the initial stress state, you will not have some good results. So this is how a numerical problem works in a 3D model. These are some piles with a cap. So if you need to reproduce it, the questions, if you remember, how to take into account the nonlinearity behavior of the soil. You see that the soil, the colors are the level of plasticity within the soil. The plasticity induced by the load applied to the pile, to the group of piles here. So you see that the behavior, it's definitely not nonlinear. You have plasticity that is evolved. If you have plasticity, that means that it is not linear. So the question is how to take into account this non-linearity of the soil at the interface. First question, do we have an influence of soil parameters with the thermal variation? We know that for sand, it's mainly well addressed. We know that it will not change for sands. For clay, it depends. That means that we need to take it into account. The influence of thermal loading, as I told you, and the influence of boundary condition of pile head fixities. First thing that we can do, don't be afraid of this equation. I'm not going to talk about them, but just to let you know what we do in numerical modeling. We have two ways to do it. The first way is to say, okay, if I go back, I want to take into account the fact that the soil could behave in a nonlinear way. That means that we need to implement a constitutive law that take into account this nonlinearity. You have in the literature, and depending on the software you use, you have various number of soil constitutive models. Plaxis, Bruno, you have this on Plaxis. You have this hardening soil model, small strain model. What other? Morcoulon is the easier. Morcoulon is the easier one. Thank you, Christina. But the problem of Morcoulon is that it's a purely elastic, perfectly plastic model. That means that, and this is really why I wanted to have something to draw, but it's okay. We know that we need to take into account this nonlinearity. How to take it into account? First, in the elastic part of the behavior. a soil behaves if I do the behavior of a point. If I take a point and I draw its behavior, how it behaves. If here it's this axis, it's the stress, and here the strain. How does it behave, a soil? A soil, you know that a soil has a very strong non-linearity. It will start by a linear, then non-linear, and then you will have some hardening, positive or negative hardening, okay? A non-linear behavior. So even on the elastic part, the elastic could be non-linear. Why? Because depending on the depth, you see, the elasticity could vary with depth. Before starting the calculation, imagine that you have a uniform soil. You cannot say that the Young modulus of the soil, the elasticity parameter E, the Young modulus, you cannot say that E, it's the same at the surface and 20 meters below. Why? Because the initial condition have led to have, let's say, a stronger and then a higher value of E with depth. Mainly, in our model we have developed, that I have implemented in my code, we have developed, this is a local code, we call it mod-sol, model soil. It was easy to call it mod-sol, because I cannot say Mroueh or Hussein Mroueh, I don't know why. So mod-sol, it's convenient, okay. So we use this kind of elasticity. Then, for the plastic part, we have several things to take into account. You remember I said that the plastic part, it becomes like this, and then you have this hardening, yes? You know what is hardening, okay? In order to reproduce this hardening, you need to have a surface load. This is the equation of the surface load. This is a mathematical equation, F. F controls the plasticity. If I draw this in this plane, Q is what we call the deviator of stress, and P is the mean pressure value. In the PQ plan, we have this monotonic surface load. It's this one. When you do some calculation, you do a calculation and you calculate the stress. When you calculate P and Q for this point, if you are here, that means you are on the elastic part. So this is the equation that will control the behavior. It's easy. So it's elastic, it's one iteration, you have the solution. And if you continue to load the pile, what would happen? At a certain level of stress, you will reach this initial elastic domain here. Here, for this line, F become equal to 0. When F is equal to 0, that means that you are in plasticity. When F is less than 0, you are in elasticity. So you do your calculation, your finite element calculation. This is done automatically by the code. And the code calculates the mean values P and Q. And if you are here, elasticity. If you are here, plasticity. And once you are here, what could happen? So this is Mroueh. This is Mroueh. Mroueh, you will not move this hardening. That means that once you reach the plasticity, it becomes constant. And with Mroueh, you will never be able to reproduce. You remember what I was saying? You will never be able to reproduce the degradation, especially the degradation of the soil around the pile. You will never be able, because for Mroueh, it will be a reversible condition. It will be elastic, plastic. If you reduce the load, it will reduce in an elastic way. If you reapply, you will develop the same amount of plasticity. The plasticity will stay constant. It's definitely not good. We introduce a parameter that controls this parameter Rm, that control what we call the hardening. The hardening, it's if the soil if the soil increase, you remember this, up it increase, this is the hardening, and sometimes the decrease of hardening, the softening. So Rm is a value that is moving from 0 to 1, depending on how you develop. You have some mathematical expression that is controlling this value. I'm not going to give it, but this control the hardening. What does it mean? It means that once you are here, this domain will be pushed by the plasticity. It's like this line. In the deviatoric stress plane, it's better, you can see it. It's like, this is the domain I'm talking about. It's like this domain is growing. It is growing because of the hardening. What I'm drawing here, it's exactly this. If you cut, you see the 3D representation. This is the 3D representation. So remember, if you are here, elasticity, then we reach, and then this plane, this line will be moving like this. This is what we call isotropic hardening, to take into account the fact that we may have a hardening or softening. But it is not sufficient because of the cyclic effect now. What could happen with the cyclic loading? You remember, I told you, at a certain amount of cycles, you may experience some degradation. And if you want to reproduce it, you need to add a cyclic surface loading. This cyclic surface loading now, it is controlled by this second equation and this second parameter, which is called the kinematic hardening. So you have two kinds of hardening, isotropic hardening and kinematic. Kinematic, first it was this one that is moving, and the other it's expand or not. And then you see from the beginning to the end, you can have something that is moving in all the direction, growing, slowing, and moving like this. This is the hardening. And if you are able to introduce all this, then you are able to reproduce the more or less something that is close to the reality for the soil behavior. But it is really not obvious. Why? Because you need, if you want to do this, in some constitutive models, you need to define 12 to 15 parameters. And these parameters need to be calibrated. You cannot use, because each parameter have influence on the behavior. How to calibrate it? You can calibrate it with calibrate these parameters with the measure you do on the field, or with some samples. You take some samples, you do some triaxial test, and you try to calibrate these 15 parameters. It's very complicated. You cannot ask an engineer to do like this. It will be too time consuming. It's really complicated. In research, we try to do it. But at the end, do we really need to reproduce this nonlinearity in our case, in the case of energy geostructures? Do we need? In reality, no. Why we don't need? Because if you, again, take a look here, mainly where the nonlinearity happen. The nonlinearity happen mainly at the interface between the soil and the ground, at the interface. And remember, we are extracting how many temperature, what is the delta T value on energy geostructures? Between 6 to 8 degrees. On this amount of, on this range of temperature, the deformation are very small on the ground. So we don't need to have all this complexity. But in one specific location, maybe we could have some strong discontinuities, some strong non-linearities, even in this small value, where at the interface. So instead of doing a 3D mesh where we refine the mesh around the geostructure in order to capture the deformation of the soil, instead of doing that, what we can do, it's maybe to look only on the localization of these non-linearities. We know that these non-linearities will mainly behave at the interface. So another solution in order to do something really much more easier, it's to use, as Professor Christina said, more Coulomb. More Coulomb for the soil, it's large enough. But if we do this, then remember that we need also to take into account this strong non-linearity that could behave. And what we can do, then we can introduce what we call this interface element. These interface elements are some contact elements that can reproduce several types of behaviors between stick condition. Stick contact is adhesion. Adhesion means that independently on how the pile behaves, the soil will keep sticked. Collé. Okay, to the soil. It's not reality. At the beginning, it's real, but after that, this interface element could also reproduce what we call slipping, sliding effect, and even in some cases, in some localization, in some local places, we could have some disconnection of soil and ground. And interface element allow this. And why now it's much more easier? Because we are working on a plane, not on a 3D. So it's much more convenient. So this is more or less the same model. You remember Mort-Coulomb, this is the Mort-Coulomb. Inside, stick, elasticity. Here, plasticity, it starts to slip. And then this line, when f is greater than 0, it's forbidden. We never could have it. We have to correct. So these are the iteration you have. The person who do calculation. When you see some iteration, it's because you do a calculation, you reach this space, then you have to come back here. These are the iteration. And then this line, as I told you, could behave, could move, and instead of having this non-linearity on the soil, we have this non-linearity on the interface. This is what we have developed. Also, we call it, you remember, mode sol for the soil, here mode joint for the joint. This is also a model we use, like exactly the same. Isotropic hardening parameter, you remember. GR is the isotropic hardening parameter that control, you remember as I told you, this is the Mort-Coulomb. It starts from Mort-Coulomb, then it can expand. And this is the kinematic one, where it can move at the interface. And doing this, then we are able to take into account the hardening and the degradation of the interface at the soil pile or soil wall interface. And this becomes really interesting because in this way we can estimate what could happen after 50 years of cycles. Daily one, monthly one, seasonal one, heating, cooling, over years. Otherwise, you will always have the same result and you will never see something. And then this is what we try to reproduce with different type of thermal loading. Uniform one with a rest period, sinusoidal one. It's just a calculation. And you see, these results show that you have a kind of at the first steps, it behaves, and then it becomes to get harder and harder. So we can estimate better the results. What we show here, we are not going to go into details. These are the induced displacement. The induced displacement. We see that the thermal cyclic loading has a very high influence, and this is why it's really important. And this is exactly what Bruna was showing last week. This is really important. And we now have the right tools to reproduce it. But it is still too much complicated to do like this. It's complicated. So what we try to do, because we have some partners, Pinto, we have some partners that would like to have a more practical tool, engineering tool, where they don't want to have a 3D calculation, finite element calculation, because it's time consuming and so on. They would like to have a very easy tool, let's say. So we have developed with one of my PhD students a new 1D model, which is close to, I don't know if you have ever heard about this subgrade reaction method, TZ model. You know TZ model, yes? I don't know if the students know. No. Yeah? Okay. You have this. But in our TZ model, in our TZ model, we introduce something new that is not taken into account in the conventional TZ model. We have introduced something new. We have introduced the fact that when you see the problem, we model it with some 1D element, bar element, and on each node, we introduce two types of springs. Not only Kt, the friction, but only Kn. Why? To take into account the variation of the normal stress along the pile. On the TZ method, this is not taken into account. The TZ method do not take into account the fact that the normal stress could vary with this. So we enhance this. This is a new tool where we have this variation of Kn, and then we have this plasticity that we are talking on the springs. We put it on the springs. We have to solve something like this. This is the algorithm we did, and these are the results we obtained. These are the results of conventional TZ method. These are our results. You see that it may be the same, but look the nonlinear in comparison with this. This is the new one integrating Kn and Kt. These are the conventional one where you have only Kt. These are our results where you have Kn. These are the experimental results, like yours, Christina. And this is the numerical modeling we had. So it works much more better than the conventional one. And even with the cyclic loading, you see the points are our numerical results. We have quite very good, more or less, but it's quite very good. This is the delta T, and this is the relative displacement. You see, we have more or less the same trend, depending on the level of load applied on the pile, the mechanical load. This is the mechanical load. So these are our results. We are on the conclusion. Still finish. So why we need to continue now the work? We know that we have some limited studies on the performance of energy geostructures in unsaturated soils. We still need to work on it. There are what we need. We need to develop some preliminary charts, to better understand and estimate the amount of energy extracted or injected in the soil depending on the groundwater level. This has not been done. What has been done previously, it's in saturated soil. So we aim to do the same for unsaturated soil. We aim to study the thermohydromechanical response of energy geostructures in unsaturated soils. And when we are talking about unsaturated soils, we have to take into account also, if we talk about the chalk, that it's no more a soil, but also a soil with some void and non-saturation partial. So it becomes a porous media. So the equations are not really the same. We have to take it into account. This is what we do. And after that, to be able to study the long-term behavior of energy in unsaturated soil. These are, taking into account these recovery period, exactly what you have also, Christina. This is what we do. And also, as I told you, the spatial variability of the characteristic of the ground, because we estimate that everything is constant, which is not really the case. We have several questions to deal with. You see, if this is a typical lithology of the Paris Bassin condition. It's very complicated. So when you do a thermal response test to estimate a value, it's more or less a global value you obtain, but you don't have this variability with this. It's really complicated. So how to measure the thermal properties when you have something like this? You have different possibilities, the thermal response test, the laboratory test, but all of these are impacted, or for all of this you have some issues to overcome. So it's really complicated. And also you have to take into account on the fact that you are not having conduction, but also advection could happen. And this could influence the value of lambda C that you measure. So this is really challenging. So if I come back, what is the influence of this regional heterogeneity of the permeability distribution? What is the influence of the stochastic permeability distribution? Because we know that we have this stochastic permeability distribution. What is the influence of the time-dependent stochastic permeability distribution? Because it's also changed with time, depending on the season. And what is the influence, as I told you right now, the variability of the thermal conductivity coefficient. Within the same formation, within the same soil, we could have a variability of the value, depending on the water content and so on. So these are all what we need to do, and also how to integrate all these interactions that we have. As I told you, the interaction with the atmosphere, the interaction with the interior air in some cases, how to integrate it in the numerical model. These are our challenges that we still need to overcome with all the tools we are developing. Muito obrigado por sua atenção. Thank you very much. It was maybe intensive, no? Sorry.
No, you can take some water.
Yes, it's okay. I still have some
also
power.
Sit,
No, I will sit. If I sit, I will not be able to.
And your talk.
The question is are welcome now.
I think it's the time of questions. Excuse me, Pankaj.
Hello, good afternoon, sir, Professor. I have two questions. One, for example, if we are dealing with the area where pile is not suitable, pile foundation not suitable, like I belongs to a
India.
area, India where it's a hilly region, mountainous region, and it's a rocky strata. So is it possible to install a geothermal solution there? Such strata?
The message we would like to promote, it's the one. Wherever you install piles, just put some tubes inside. You remember these tubes to exchange. Even if they are not connected to a pump, just install the tubes. Why? Because once you have installed the pile and build your building, it's finished. You will not be anymore able to use this pile for the future. And what is the cost? The extra cost? It's only this PET tubes, less than 1% of the cost. So what the message we would like to really promote, wherever you are in the world, just install these tubes and wait. Maybe one time will come and then the owner of the building will say, oh, yes, I know that I have some tubes. Now I can connect just these tubes with a ground heat pump and up, I will be able to extract. Maybe now you are not concerned, but India is the second most populated country in the world, over 1.4.
No, it's 1.4.
Yes, 1.4 billion. Yeah. I cannot imagine that you are not concerned. For sure you are concerned, especially with one type of use of these energy piles, what we call, you remember I was talking about it last time, how do you remember? What we call geocooling. You remember or not? You know, geocooling is the use of this without heat pump. It is just circulation of air, and it works. It works. We have an installation. I talked to some of you that we have a gym room in my university. We have a gym room where we practice sports. And this room is equipped with geocooling. That means that only without heat pump, it's only extracting the temperature of the air to refresh the place. At least it will cover a part of the energy need for refreshing a place. So for sure you are concerned.
No, my question is like, for example, I belongs to such area where we usually not use pile foundation. So my question is, if we don't have pile foundation.
No, if you don't have pile foundation, you are not concerned. Yes, you can use what you use the conventional. The conventional, either boreholes or horizontal one.
Okay.
But then you will have this issue of land use and some other issues.
Yeah, because we have
yes,
hot
for sure.
spring in some area, but it's a rocky strata. So there are lots of hot spring in Himalayan region. But it's a rock.
But maybe you are talking about piles, but what about retaining walls?
Yeah, maybe retaining wall. And second question is, when we are talking about non-linearity, so we can consider, we have a limit of considering number of parameter, I think, because as we are considering 2 parameter, let's say shear strength parameter, so someone will told you just consider one more, consider water, consider heat, consider this, and it become obvious that every model become a non-linear. So so what we consider that linear model are wrong, considering taking into account some parameter and saying if it's a linear, then it's not a right way to analyze the things.
This is for the ground.
Yeah, my question is just if we are using a linear model.
Yes, I understood.
So that's
if you are using a linear model, then you will not be able to capture or to reproduce what will be the evolution of the contact condition between the ground and the soil, for sure. And you will be able to estimate the amount of the strain and stress induced by heating, because the amount are very small. We are on this elastic part, for sure, at a global scale, but at a local scale, you will not be able. And the main concern of the builders and even of the design offices, are we sure that these cycles will not be degraded so that the performance of the pile will be lost? And because of this question, what they say, oh, it's too complicated.
Yeah, it's very complicated.
Yes, and then that's why they say, no, we don't want to install geothermal tubes in our piles because we are afraid that it will perturb and it will disturb. It will disturb the behavior. So that's why it's important to be able to have some efficient tools, powerful tools to calculate what would happen with some challenging soil condition. Maybe most of the soils are not challenging and it's easy to answer. But in some particular case, we still need to address this issue. Yeah. So, and this is the only way for us researchers to encourage our builders, contractors, and so on to implement, to convince them that we know that even when we use some very powerful tools, we can demonstrate that everything is going well, and then they will be okay. They will be fine, and they say, okay, we are convinced. Then we can install. It's the only way to convince them. You cannot say, no, don't worry, there will be nothing. And what will happen in 20 years? Don't worry, you cannot. You have to have some tools that demonstrate it. Okay. This is what we do.
Thank you. Thank you, Professor.
If someone have other questions?
Felicitations, Professor.
Thank you.
I have a question about the practical part. I have some concerns or doubts about how expensive is the maintenance of the tubes that are embedded in the piles, and also how complex do they require a special manpower, and how expensive is the cost compared to the cost of the pile construction, of the materials.
Thank you, Ronald. Good question. But I'm a geotechnical engineer. I'm not an expert. No, but I have some answers. Don't worry. There is no maintenance because the tubes are embedded in the concrete. After they are embedded, they will never experience any disaster. They are totally embedded. The only maintenance is the maintenance of the heat pump, like the maintenance of this. So this question have to be answered by some thermal engineers or yes. Then the cost of the pipes. Then now we can talk. The cost of the pipes. It's plastic. It's PET tubes. It represents even if you use for an installation like some of what we are doing. You know, we have hundreds of meters of pipe. It's maybe sometimes kilometers of tubes. But how does it cost? Maybe 1% of the global cost of the pipe installation. So it's not really an issue, the cost of the tubes. The maintenance, yes, but the maintenance of the heat pump, the systems. If you know, when you install these tubes, the first thing before they continue, when they put the concrete on these tubes, the first thing they do, it's a kind of impermeability test. They inject a certain amount of water, and they measure the amount of water that is going out. And if you have the same, that means the system is impermeable. You have no loss, no degradation, and then you can cover it, and it's finished. The tube is inside the concrete, and it will never be. It will never have a.
So the tubes are not a problem in terms of maintenance.
No,
mainly
the
pump.
Yes, and maybe some parts of the tubes, but that are already outside the system. Mm-hmm. But then it becomes,
so it's not so expensive.
No.
Finally.
No. Really, the problem is not there. The problem is.
Yes. Because most people may have some doubts about that, mainly because of the cost. That's the first question that
you see the amount of tubes you have. So the only thing is the tubes that are going out. Maybe here you can experience some problem, but here it's easy. You excavate, you repair, and it's finished. It's like when you have a plume in your home. It's quite easy. I can do it. So if I can do it, it's easy.
Merci beaucoup, Professor.
You're welcome. Thank you, Ronner.
Thank you. Other question, if you want to ask in Portuguese or French.
Professor, thank you for the presentation.
Thank you.
Congratulations. It was very good. And I have a doubt. We have a lot of factors that influence the systems, but in fact, does we have any case of rupture or a big problem that may spend a lot of to the structure? Like, do we have cases of any problem involving this technology? We have thank you for this question. We have a very important issue during the installation of the system, because as you see, where are these pictures? There, as you see, during the installation, all the workers have to pay attention of these tubes. And if they break the tube, the system will not work. And this often happens. Why? Because conventional civil workers do not pay attention of this. You know, it's some of you that have already been in a field, you know how complex it's a field. And when you tell them, okay, you put the concrete, but then after this, you know, you have a part that you have to cut. But pay attention. If you cut it, you don't have to touch the tubes. And therefore, it requires like 3 times more effort for them to pay attention to avoid accident. And sometimes they say, oh, it's not my problem, and it could happen. So yes, and if it happens, it's really a problem. And what could happen at that moment is then the owners come and say, we stop the construction, you repair before we continue. So it could happen, yes. And it is, until now, one of the major issues we have to overcome. And that's why even when we talk with builders, they are convinced about the global performance and it's good because we are saving CO2 and so on, everything. And then when they start thinking on the operational part, how many efforts they need to protect these tubes and so on, it's a quite good question. They know that this will in fact have a cost. Not the material, but the human cost will increase due to the attention they have to pay on these tubes. So this is an issue, you are right. And this is why they also, but engineers are also here to adapt to the situation. So they have to adapt themselves to the situation. They have to develop a new way on how to protect and so on. It's not, at the end, it's not an issue. Engineers are also here to find some solution, not to say it's a problem, then we will not do it. Every problem has a solution.
It's a high density pipe.
Yes, it's yes.
Very small.
So
There's some problem of strangulation
yes.
into the loop, so
Yes, you see these all these angles. It's
you just check the angle.
if you. So it's an issue, but the cost, Ronner, coming back to your question and your question again. So the cost, it's not the cost of the material, it's the cost of the human time.
Got it. Another question. Does it works the same way for extreme condition weather like Canada, North Canada or something like this?
We have a field in Romania, not this one. Yes, I didn't put it. Yes.
Norway, yeah.
Yes, it works. Where we have one colleague, Martin, who is implementing it in Norway. It works. It works. It works, but it cannot maybe cover all the need of the building, but at least it can cover from 30 to 50, 60% of the need, but it depends on the density of piles, of energy piles you will implement within all the piles. But it works. It's not a problem. It's a thermodynamic problem. It's a delta T. It's a delta T problem. In some cases, depending on the energy demand of the building, what could happen is that the need, what is provided by the system, could not be enough. And for a building, we are working on a hospital in Romania where these piles have been installed, and most of the time, the energy demand of the hospital, if it's a real case of the hospital, is provided by the piles, 100%. But in some extreme case, as you are saying, in winter, this system are supplemented with other systems like aerothermal heat pump, like this one. Hybrid. This is what we call hybrid system. In all case, it's a very interesting case of using energy geostructures in combination with others, because the heat pump need electricity. Yes, you know what is a heat pump? Ground heat pump need electricity. Okay, so in all case you consume electricity, but when you have a COP coefficient of performance of 4, when you use 1 megawatt of electricity, if you have a COP of 4, with these systems you have a COP around 4 to 5. When you consume 1 kilowatt of electricity, 1 megawatt, sorry, or 1 kilowatt is the same, you produce 4 to 5 megawatt. So it's interesting. Okay, from the soil. Okay, this is the COP. This 1 megawatt that you used for the need of the electricity for the heat pump could provide from where? Could provide from photovoltaic panels.
Solar energy.
Photovoltaic panels. Then then it becomes
cheaper.
Hybrid system.
Yeah.
Photovoltaic provide the electricity for one part of the heat demand. You see, but not only. You can also use some solar panels. solar panels, it's used to for what? I see it very much here. It's for heating the water, no? You remember we want to heat the water on summer. The more the water is heat, the best is the performance of the system. So instead of using the heat pump for heating the water, if you use the solar panel will heat the water, and the water that will go in the system will be heated by solar panels and will go out with a lower temperature and will give cooling for the building, and it will cost nothing. So you see, so this is why we try to install these in combination or integrated with other technologies.
Okay.
And another thing, I didn't talk about it today. We said that it is used for heating and cooling, but it is also used for storage.
This is interesting.
Storage, why? Because imagine you have a data center here in this campus, no? You have certainly a data center. You know that data center requires many energy, and they also, because you know that you have this heat produced by the computers. You have a very big amount of energy that is extracted from data center and that are going on the air for heating the birds. But this energy, if you use it, if you capture it and you put it on the soil, you can use it. You can use energy geostructures to store this heat, and then to use it for what? When you need it for the next winter. So this is also a topic. One of our within our European project, we have some colleagues. Fleur Loveridge. Some of you maybe have met her. She is working on storage of the potentiality, the storage potentiality of this technology.
And the last question. We saw that we can use in different kinds of soil, like you said, chalk and quick clays, and this is very interesting because in Brazil we have a variation of soil. But when we are talking about rocks, it works very different.
Yes.
That's studies about it.
Yes, the same. If in this rock you don't need to put piles, there is no question. But if you have a wall that could interact with the rock, you have some other issues. Mainly not the deformation of the rock matrix, but mainly the behavior of the fault, of the fracture you have inside the rock.
Okay.
And this become another problem. But this has not been already, in my knowledge, this has... Yes.
And they installed energy pipes, a loop
in rocks. Yes, it works, but then you have some other issues about the presence of of these fractures within the rock mass. So the main issue could be the behavior of these fractures instead of the rock matrix itself, which is not really the same with chalk. Chalk could be assumed as a rock soil, but also as a rock, as it could be assumed as a soil. And in our case, it looks like a soil.
Okay. Thank you so much,
Thank
Professor.
you.
More questions?
But I'm here until
You're
third
already
day.
here. He's tired.
So no, I'm not tired. It's okay. So maybe people want to leave. I don't know.
Okay, but if you ever have more questions, and the
Do not
Professor
hesitate.
Hussein, you'll be here until
Third day.
Thursday.
So it will be my pleasure.
Have more 4 days of Professor Hussein in the technical department. So free to, in the visitor professor rooms. He's there. And thank you very much.
Thank you, Christina. Thank
It
you
was
again
a
for this.
pleasure.
Thank you for this
Having you.
invitation. Thank you so much for giving me this opportunity to discover Brazil. It's my first time in South America, in Brazil. Wonderful
Nice.
place. Thank you very
Thank
much.
you.
Last thing,
I'm still looking for a T-shirt like this, USP. I want one.